All right, here we are on page 2. So, question 6. Determine if the following probability distribution is valid. If it is valid, then find the mean and the standard deviation. If it's not valid, then explain why it is not. All right, so if we add up those probabilities, 1/16 plus 1/4 plus 3/8 plus 1/4 plus 1/16, if you add that up, that adds up to 1.0. So therefore, we do in fact have a valid probability distribution, right? So if I go 1/16 plus, that would be 4/16 plus, that would be 6/16 plus 4/16 plus 1/16, that equals 100% or 16/16. So therefore, yes, it's a valid probability distribution. So therefore, if it is valid, find the mean and the standard deviation. So remember, we could do this by hand, right? We could multiply these together and add them all up. But instead, we're just going to go stat, edit. There's my values, 0 through 4, and there's my probabilities. So we're just going to go stat, calc, 1var stats on list 1 and list 2 simultaneously. We calculate it, and I have, there's the mean, and there's the standard deviation. So the mean is equal to 2, the standard deviation is equal to 1. And you're done. Question 7, we had to skip question 7. Question 8. Assume the gestation period of humans follows a normal distribution with a mean of 266 and a standard deviation of 16 days. Using the empirical rule, what proportion of pregnancies last between 282 and 314 days? So remember, if I look at a normal curve, then I know that 68% of the observations lie within one standard deviation. So if that's one standard deviation on either side, then this adds up to 68%, which means each of these little pieces is 34%. Well, then if I go out one more standard deviation, that gets me out to 95%. So if I take 95 and subtract out the 68, that gives me 27% left over for these two pieces. So that means this is 13.5%, and this is 13.5%. Then I go out one more standard deviation, and that's 99.7%. So if I take 99.7 and subtract out the 95, that gives me 4.7% for these two wings. So I got to cut that in half. That gives me 2.35 and 2.35%. Okay, well, where are we in this problem? It says here's the mean at 266. 282, notice if I take 282 and subtract out 266, it gives me 16. That means this is one standard deviation right here above the mean. So that's 282. If I go up another standard deviation, that gets me up to 298. And if I go up one more standard deviation, that gets me up to 314. So therefore, what proportion of the pregnancies last between 282 and 314? All of these guys. So the answer was 13.5% plus 2.35%, which gives me, what is that, 15.85%? And we're done. Number 9, assume the distribution of boys' times for running the mile is normally distributed with a mean of 6.2 and a standard deviation of 0.4. The distribution of girls' times is normally distributed 6.8, standard deviation of 0.3. John runs a mile in 7 minutes. So his z-score, remember how many standard deviations above the mean he is, or away from the mean he is. So what is his score? He ran it in 7 minus the mean, which is 6.2, divided by the standard deviation, which is 0.4. So that gives me 0.8 over 0.4, which is 2. So he's 2 standard deviations above average. That's not very good, because remember, we want to, if we're trying to run the mile, we want to run it in a short amount of time as possible. And he's 2 standard deviations above average, which is slow. So what about Jane? Her z-score, she runs it in 7.3 minutes. So that's going to be 7.3 minus the mean, which is 6.8, divided by the standard deviation, which is 0.3. So that is 0.5 divided by 0.3, which is 1.67. So she's also slow, but she's not as slow as John is, right? Because she's closer to the average. She's above average, which means she's slow. John is above average, but he's slow too, but he's further away from his average than she is from hers. Therefore, Jane is better, because she is not as slow as John is in comparison to the rest of the population. If you thought about this in terms of probabilities, if I go to the distribution and do normal CDF from 2 to infinity, that means that John is only 2% of the people run slower than John does. And if I do Jane from 1.67 up to infinity, 4%, almost 5% of the people run slower than Jane. And a lot of folks had this idea turned around. They said, oh, the z-score's high, therefore John's better because his z-score's higher. But you wouldn't want to have a high z-score for your running times. You would want to have a low z-score so that you're below average time, not above average. Number 10, if the distribution of a random variable follows a normal distribution with a mean of 8 and a standard deviation of 1.5 in the population, and you randomly sample 25 observations from that population, would you be surprised if the average of your sample was as large as 9? Explain your reasoning and show your work. Well, at first glance, you go, oh, well, that's not very far away from the mean because the standard deviation is 1.5. This is only 1 point away from the average. Seems like that should be relatively common. But remember, I'm not going to use this as my standard deviation because I'm taking a sample of size 25. My standard deviation is going to be 1.5 divided by the square root of the sample size, which is 25. So 1.5 divided by 5 is what? 0.33? No, it's... Why can't I think of that one? Clear. 1.5 divided by 5 is 0.3. Oh, there we go. So that's one standard deviation now, not the 1.5. So now let's think about this 9 again. That 9 is much further away from this 8 than it looked like at first glance. What's our z-score? Our z-score is 9 minus 8 divided by 1.5 over the square root of 25. So this is 1 over 0.3, which is 3.33. That means that observation of 9 is highly unlikely. It's more than 3 standard deviations away from the expected value of 8. Right? So if I randomly sample from this population, I should get a sample average of 8. And I know there's random variation, so it's not very likely that I'm going to get exactly 8, but I should be close to 8 because the standard deviation is only 0.3 for that large of a sample size. So therefore, 9 is very unlikely. And in fact, we can calculate its probability by going distribution, normal CDF, from 3.33 up to infinity, right? Because do our z-scores. Only, 0.0004, so that's 0.04%, right? So the probability that our z-score will be as big as 3.33, that's very close to 0. It's 0.00043, right? So that's 0.04%. Very unlikely that would happen.